Speaking of reliability, a podcast with good friends talking with you about reliability engineering topics. Welcome to Speaking of Reliability. This is Fred Schenkelberg.
And this is Mojan Sohi. Hey, Fred.
Hey, Mojan. We got an interesting prompt. And then when I mentioned that earlier to you, I said, oh, that sounds like I know what I'm doing with AI. But Joseph and I had reported a couple of broken links, and so we sorted that out, and then he's prepping for CRE and enjoying the website and stuff like that. And he just in random on his message, he said, quote, "I wonder what leaps and bounds reliability engineering will have to make when we go to Mars. Maybe nothing new or amazing, but a very thorough implementation of failure modes analysis of what we know. But then there are the unknown unknowns, ... And I thought, and then end quote. Well, that's an interesting notion. And it's another one of these T-shirt moments for you, so get your pencil ready. Is one of the reasons I really like reliability engineering is it doesn't change all that much. We have FMEAs, that was in the 50s. We have block diagrams, that was in the 50s. We have fault tree analysis, that was in the 50s. We have physics of failure, that was started in the 50s, early 60s. We had Weibull analysis. Weibull wrote that paper in the 50s. And on and on and on. And control charts from the 20s, like they're over a century old. And vast majority of the primary tools we use is nothing earth-shattering or new or novel or whatever, despite all the academics at conferences going, well, if you look at this fault tree, when you hold the page up at an angle and get the light just right, then it does this. Right?
Yeah.
You've been there. You saw those.
You just gotta squint.
Yeah, squint and wave your hand and use a fancy term and a weird symbol on it, and it's new.
Voila. Totally new.
Yeah, no, it's not. It's such a corner case nobody ever uses. That's one of the benefits is our techniques, the methods we use, haven't really evolved at all. And so what will it take to create something that's super expensive, complex, and has to work for 5 years without fail if we're going to put people inside a capsule to send them away for 6 months?
Not to mention that it's something expensive, right? At the beginning, it's going to be very expensive. So it's to your point earlier, I don't think we're not going to have the luxury of I think a lot of people, when they think about reliability testing, they think about testing. This is not going to be something that we are going to have the luxury of to be able to test a lot, just because of the cost. So,
well, my preference, and I'm thinking to the NASA in the 60s, and they started off with a single person capsule that, basically jammed them in there like a sardine and just go up high enough, come back down, let's hope the parachute works. And then Gemini was 2 people, and they did a spacewalk, I think, they stuck their head out of the capsule and stuff like that. And it took them 10 years, but in 10 years, they went from, oh, if somebody put a satellite up there, we got to get to the moon first for whatever reason. And they did. But it was, between Mercury and Gemini and the early Apollo was a lot of testing, and they basically just worked. There were a few problems and explosions, and they had, safety things that did. They had an ability, if the rocket was bad on the launch pad, that they could rocket off the capsule and save people, or they had a zip line they could jump into and get out if they could get out of the capsule, stuff like that. But it wasn't like they had 30 rockets that they launched one a month to see how far it would go and then learn from it, like what SpaceX is doing now. I mean, SpaceX has launched more rockets, I think, in this year, in the first couple of months of this year, than NASA ever did.
Really? Wow. That's amazing.
I'd have to double check it, but I saw a map where they're launching like every other day or every 3 days.
Wow.
And most of them are, putting up satellites and doing other space junk up there. But that might be a whole nother realm of reliability is how much space junk is up there.
Wow, you are right. I just looked it up. As of March 10th, 2026, SpaceX has launched 30 Falcon 9 rockets this year.
Yeah, yeah. They're just
Incredible.
cranking them out. And
Yeah.
I think I saw one that was that because they land it and refurbish it, put it back on the launch pad. They have one of them that's done it like 15 times or something like that.
It's so fascinating, like, to think about rockets as being repairable systems.
Yeah. It's just a big chunk of
It just,
steel, you
it,
put everything
yeah,
in.
yeah, yeah, yeah. I mean, or maybe it's, I don't know, I'm sure it obviously has some composites in there, but yeah, it's just so interesting to think about them as repairable systems.
Yeah. And I mean, the boundaries and the barriers and so on, back to Joseph's questions, aren't anything really new to what most of our tools can implement and do. Yet and the other one is I think it was the Curiosity rover or was one of the other ones. They expected it to last, only a certain amount of time. It was like a month or two, and it's gone 15 years, done all kinds of stuff, just keep rolling around. And it was the last message the rover sent back. It says, "My batteries are critically low and it's getting dark." It's just like,
Mm.
oh, you poor little
Oh,
thing.
oh, oh, yeah.
Sandstorm came and
It's a
covered it.
sad message. Yeah.
Yeah. But it was the and I knew some folks at JPL and they were very pleasantly surprised. One, it worked, and two, it worked for a year. They were just, how is this happening? Now they got to figure out funding to keep the staff going, to keep exploring and keep doing stuff. They did not plan on it
Expect.
lasting
Yeah.
at
Yeah.
all more
Mm-hmm.
than a few months.
Mm-hmm.
And the amount of stuff they learned and all the stuff they did was amazing. But right, there was nothing particularly unique about how they approached the reliability of it. They designed for the environment they expected. They had designed some contingencies, some backup systems, and especially in the communications type stuff, but enough resilience that if it ran into a boulder that they didn't plan on, it would stop autonomously, not just try to, roll over it or try to get, it would wait for further instructions. But if we're putting people in a capsule to Mars, we don't get that backup. The time delay is not acceptable if there's a leak, if there's a problem, if there's a
Right. Which means I guess like that there's bound to be lots of repairs in situ, right? Like you need
Mhm.
to be able to do on-site repairs. Hopefully, some that are essentially automatic. I would imagine uh, you know, thinking a bit, maybe this is a bit sci-fi, but uh, there's bound to be lots of the utilization of lots of sensors, right,
Mhm.
on the system to be able
Yeah.
to detect just this damage monitoring has got to be a thing,
Yep.
for a system like this,
Yep.
and for it to be able to automatically detect, what's happening if there's something that is looking like an outlier and it's being damaged faster than expected, and then to be able to automatically repair itself too. In many cases, I would think that has to be a part of it.
Yeah, you see that in science fiction. It's like something
Hmm.
hits a window on a space station and then it just kind of seals itself. Like, okay,
Hmm.
yeah, that always happens. Yeah, okay, cool. But
Yeah.
also the trade-off is all of those extra sensors, all that extra computing power, all of the spare parts are all weight. And it's how are you going to look? It might be three or four rockets up to a place where you assemble the kit and then you take off and go to Mars because it's a lot easier to move in space than it is off the surface.
Yeah.
I think that was why people were looking at going to the moon because it would be easier as a launch pad, especially if they could get water and fuel there.
Yes, exactly. You need a like a to be able to do resupply missions without having to go like completely in and out of orbit. I would imagine every time you need to like send something there.
Yeah.
So somewhere like the moon seems like the easier option to be able to do that.
But then you got more of these unknown unknowns. It's like, all right, we're making fuel from moon dust. Okay. What possibly could go wrong? You know, it's just the ability. I mean, engineers are great at
Mm.
thinking of all you just get a couple of creative engineers together and do some brainstorming, and you'll never build anything because it would be too scary. Um, and so it's yeah, we can anticipate all kinds of things, yet it doesn't cost a whole fortune to send an equivalent orbit, equivalent, size of a piece of equipment unmanned, but sensored up to find out what the hazards are. What are the environments? How does this radiation that is away from our envelope of Earth uh, really affects everything that's going on? All those kinds of things, and then send up a brave solar tool that will give it a try.
Right. And there has to be, as we just normally do in DFMEs, there's got to be, obviously a differentiation between like, okay, these failure modes just absolutely cannot happen, basically.
Hmm.
Or if they happen, it's essentially like, catastrophic and it could result
Right.
in loss of life, which would obviously be horrible. And then other failure modes are like, well, okay, like how much time, that could be like a degradation thing that, gives me some time to be able to react to it.
Right.
And it's not necessarily immediately catastrophic. And so there's got to, obviously you have to think about what to do for those super high severity ones and how to prevent those, which
Yep.
to your point earlier, I think would mean probably, that's where you're going to, if you're going to have to use up your weight distribution, you're probably going to allocate more sensors to and analysis to those things than the other failure modes
Yeah, because if you have
and
time to get back to
redundancies.
Earth, let those computers and engineers
Hmm.
help you.
Yeah,
Whereas if it's no, I got to fix this now. You
yeah.
have to have the right equipment. Now that's part of the maintenance part of it, right? But we know about maintenance. We know about repair systems and sensoring, looking for failures or signals and stuff like that. Do you think is there anything new or different? I'm thinking of the genesis of a lot of the big tools that we use now, like FMEA and block diagrams and that kind of stuff, was in the Navy submarine building programs in the 50s and 60s. And they realized, oh, we actually need to pay attention to this reliability thing. And they basically invented a handful of these tools and made them more
Mm.
rigorous and useful. And it was also in project management tools too. A lot of that came out of those kinds of programs because it was a very large, very complex system on a tight timeline, and they had to get it right because there's 100 people in the submarine, and it's like going to space. If something goes wrong, it's really bad.
Hmm.
So but I think that goes back to Joseph's question. If we're running into one of these challenges, another way to think of it is, are the tools we use now adequate to the challenge?
Yeah. It's to your point, it's unknown unknowns. Like what are the, like, does the math work? Are there conditions where our math, like we need a new math to be able to figure that out? I don't know.
Well, I'm thinking of I mean, right now we have really poor tools, mostly because most of the time we make a lot of assumptions, right? And we simplify things down. As in, Alex did a webinar on Tuesday this week, and when this comes out, it would be last month. So if I have to time jump there real quick, well, that would be a nice tool. If we could have a time machine to go 20 years in the future and find out all of the ways that our product failed, and then we come back and redesign it. That would be way cool. Yet if what we have now is too simplified, and we've got great computing power now, allegedly, not according to Star Trek standards, but we have computers now. And vibe coding, don't forget vibe coding.
Of course. Yes. Yes.
And
Yeah.
so what kinds of tools can get rid of the assuming everything's independent that we can use. So large language models and neural networks and stuff like that can handle that. A lot of people don't trust it because we don't know how it did what it did and
Hmm.
get the answers we got. Yet I think adopting more of these tools that help us master avoid making these simplifying assumptions.
Hmm.
Because I mean, finite element analysis for mechanical engineers has helped a whole lot. I've run into
Yeah.
engineers that say,
Yeah.
oh, well, I
Yeah.
assume this is where the problem is. Well, what's the analysis say? Oh, it's not there. It's over here. Okay. And then we go test it and it's where the model said. So
Yep.
it's things like that. What tools will help us get past the limitations that our current methods have?
Yes, and to your point, a lot of the limitations for our current tools are assumptions that we make, and if we can know more about those assumptions or reduce the number of assumptions, it will go a long way in being able to improve our understanding and then have a good understanding of what the risk is, basically, so we can quantify it.
Hmm. I think the one thing that, I mean, I didn't expect that we would sit down and go, oh, here's the 15 things that will be breakthrough reliability improvements over here. But I am a little disappointed in you, Mojan, that you didn't come up
Oh
with
no.
a couple of them. But I mean, the assumption part is a piece of that. And there are bits and pieces of different tools that engineering folks are using that help us do that. The one I don't see very often, and you see it really, really rarely, and many of our tools aren't even built to handle it, is like the finite element analysis. That works great with a perfect steel bar, right? Or here's our structure, and we make simplifying assumptions about the fiberglass that's used in this circuit board, for example. If we could include the traces and the components and all those pieces on it and age it 10 years. The solder joints have cycled 10,000 times and it's gone through thermal cycling and it's got radiation exposure to it. And a lot of those individual stresses we understand or should of how it affects things and then run the stress analysis. And it's artificial, simulate the aging process and then run your stress systems. Can it still work there? The tools we have right now don't make that easy. And so I'm thinking it's going to be incorporating the physics of failure type knowledge into the simulation tools, whether it's for mechanical or electrical signaling or ability to withstand a strain or a stress that is on the, like a, a large event that occurs, how resilient are you to it? And it's so that's one area I can think of that may be our breakthrough. And it's based on computing power, obviously.
I agree. But I would say the first, I mean, I think like a lot of that does happen today already as well. Like we know, I mean, at least in my experience, we've
Hmm.
used degraded material properties in simulations and the virtual tools to understand how does it perform, after the material has degraded and it's been aged.
Hmm. Well,
I
that's
think
good.
the yeah, but I think that prior to that though, I think that we do need new materials. Like that's going to be the first thing I think is going to be like a lot of the existing materials. Um, I think like you said, like we need optimization around weight. Like weight is a big restriction.
Hmm.
And I think one of the big changes is going to be now, whether it's strictly reliability engineering or not, I don't know, but material engineering may want to think otherwise, but I think the first thing is going to be the what AI and large language models and just more compute power enables is going to be inventing new materials. That is, I think, going to be one of the big things that will be improving and pushing, accelerating this advancement, because I do think we're going to need new materials for lots of things,
Oh
for
yeah.
weight optimization, for thermals, for just yeah, obviously like
Radiation
radiation,
ability.
yeah, exactly, for being able to, for repairability, for you can't exactly weld on Mars necessarily very easily, and for talking about the like there's some work on self-healing materials, but it has a long way to go.
It does,
And
yeah.
that I think is going to be like, big advancements there in that area are going to be needed to be able to, um, yeah, sustain, basically like a city or some number of humans to be able to live on Mars.
Yeah.
Um, so,
I agree, but I cringe because the we just spent a whole pile of money putting a new roof on this house that we're in because the previous roof about 15 years ago was made of a new material, a composite, and it was made to it was a pressed fiber type thing that simulated the look of slate that was a tenth the weight. So it was weight saving, so you could put slate looking roofs on structures that weren't designed to hold the weight. And for whatever reason, this company didn't anticipate that these things would be in the sun all day in, in thermal cycling. And so after about 2 years, they start to crack and fall off. And so they became known as the potato chip roof.
oh no.
And they, of course, got sued and they went out of business and did all that other stuff. And I mean, a bird would, land on our roof and a 8 inch
Yeah.
square chunk of the tile would come ripping down it's an A-frame, so it's a really steep roof. It'd come ripping down and smash into the yard.
Oh
So at
no.
some point we said, we got to fix this.
Yeah.
In that case, it was pretty darn clear that their testing was they put it up on the roof for a couple of days and said, hey, see, it works. And they didn't let that. I don't know whether it was the binder they used or it was the UV degradation or what exactly the mechanism was. You can take a look at it when you bring your FA lab with you when you come over to
Yes, I'll
visit.
bring my microscopes and my
It's
my
chemical
analyzers
and
with me. Yes.
yeah, it's bring them all
Yeah.
over. Yeah.
Yeah,
And and then but they probably designed it as if it was the standard for the standard asphalt shingles that have been standard roofing
yeah.
for 50
Yeah.
years. And they
Yeah.
probably use that standard, international standard or building standard or whatever, to say, oh, we meet that, and thought they were good. And so part of the change in reliability is that maturity piece and recognizing that, yeah, we got to use the latest, greatest tools and techniques and aging our materials. And if we do a new material, it's not proven just because it met our old standard. It has to prove itself in this different environment over time. And that's going to be a challenge. How do we go about doing that when we got somebody that says, no, we want to be there next week. Come on, let's go.
Hmm.
Light the engine.
Yes. As yeah, very typical product timelines, we'll get in we'll push the schedule to possibly skip some tests. Or
Possibly
maybe
skip some thinking.
yeah, exactly.
Yeah, don't
Or
worry
not
about
do
that.
the
Don't worry about that.
analysis. Yeah, yeah.
Yeah,
Is that really a real failure mode? Is that
yeah,
really gonna
really?
happen?
No, no, just light it up. Come
I
on,
don't
let's
think
ship
it's a
it.
real risk. Yeah. But on that note, I think talking about the bringing the lab over, I do think that being able to analyze the materials and having the techniques that are required to be able to tell to be able to analyze if something has failed, that is also going to need to be something that should be will need to be in situ basically, because you're going
Yeah,
to need to be able to do the failure analysis on site, which means that the analyzers need to be advanced in such a way so that they are, you know, more capable and smaller in size and weigh less,
yeah,
to be
yeah,
able to transfer them. And they will need to be, to operate probably more, just simply, I think. Like right now, a lot of analyzers still require, that you have this giant tank of something, whether it's argon or some other,
right. Exotic material of
yeah,
some sort at a particular
exactly.
temperature and everything else.
Yeah, exactly, exactly. Which, that stuff I think is going to need to be simplified, which again, I think that with the advancement of materials, given the use of, more compute power, I think is going to be enabled. Um, Man, I'm so excited about this. Now, the more we talk about it, the more I'm like, oh, all these amazing things are going to happen. It's like very, very cool.
We'll get an upgrade to Velcro finally. I mean, it
Yeah.
was amazing
Yeah.
in the 60s how many different materials and types of equipment and even computer programming, all of that stuff just went
Yeah.
gangbusters. And since it was a government funded program, it all was public domain. And, imagine if somebody, had in a private company invented Velcro and realized that it was a moneymaker. It would cost us a fortune to get Velcro shoe tabs for our
Mm.
kids on their
Hmm.
shoes. It just costs a
Yeah.
fortune.
Yeah.
But it had all kinds of spin-off benefits other than just going to the moon. So I think that
Yeah.
was kind of cool. Um, if only we could get our cars to be self-healing and land after they, get in an accident and get that put back on the road the day later. That maybe there's something to learn from how they turn these rockets around.
Yeah. And I think, I wonder if it'll be like a combination of just learnings from different industries too, like
Hmm.
how fast they're able to for formula, for example, like how fast they're able to figure out what needs to be changed and at the pit and change it. And like it's just like I think there's a lot of learnings to be made from both low volume and high volume industries.
Exotic and
Yeah,
simple.
yeah,
Yeah.
exactly. And just I think the advancement again in um there's companies that are enabling faster and better simulations now,
Hmm.
like with
Hmm.
that, there's more compute power. And the same thing will be enabled for CAD, right? Like if you're able to design in CAD faster, then you can and come up with more complex designs and combine that with materials. So much will change. That will be a big delta for how we are able to prototype. And to your point, maybe we that does enable some testing. And then of course the simulation side is advancing too. So
Yeah.
much. Okay, I'm convinced this is going to be there's going to be so many changes.
There
It's
are, and
going to be
it's, in the
amazing.
reliability world is,
Yeah.
what are you seeing? What can we influence or advance or make happen? It's definitely not going to be a silo of just reliability engineers. It's going to be with computer scientists and material scientists and all the other engineering disciplines, plus human factors. How do we get a person to learn not only the 3 million switches on the control panel, but now you got to do material analyst type stuff and fabricate new materials on the
Mhm.
fly. Um, yeah, it's going to be a challenge, and I think the more we think about it and come up with ideas, the more that something will hit, and it'll make a difference.
Yeah,
Yeah.
absolutely. And this is making me think about Project Hail Mary. I don't know. Have you read the book Project Hail Mary?
No, no.
Okay. Well, it is awesome. It's about it's a sci-fi, and the movie's coming out soon, and I'm very excited to watch it. We'll talk all about it, but if I would highly recommend the book if you haven't.
Okay.
If you, the book is fascinating.
All right, cool. Well, no, no, we got a podcast and a book recommendation all in one day.
There
What a
you
deal. All right,
go.
cool. But if you're listening to this and you're like, well, what about this? What about that? Like, let us know. I think this would be a really cool topic for an ongoing discussion. So, send over your comments and ideas or what you're seeing and what you're running into, especially you rocket scientists out there that are actually working on this problem, whether you're in Jet Propulsion Lab or NASA or SpaceX or one of the other rocket companies, or in a completely different industry. And what kind of breakthroughs you're seeing that's going to change the way we go about doing reliability engineering. That would be fascinating to get more discussion on it and more people involved with it. So let us know. Head over to accendoreliability.com/go/SOR. There's a couple of ways to get in touch with us. Mojan and I and the other hosts, when we're not off watching or reading science fiction books, are available on LinkedIn and our About pages. So plenty of ways for you to get in touch with us. So we look forward to your ideas and comments. And like what Joseph sent us was just a concept or an idea or a wonder is like, I'm wondering about kind of thing. Those are fine too. They're all good stuff.
Yeah, absolutely.
All right. Well, thanks so much, Mojan, for entertaining this question. And well, I'm sure we're going to talk about this and variations of it for a while now.
Yeah, absolutely. Thank you. Thanks for bringing it up, and thanks, Joseph, for sharing your thoughts.
All right, cool. Thanks so much, Mojan. We'll talk to you again soon.
Thank you.
Cheers. Thanks for listening to Speaking of Reliability. We invite you to join the conversation. If you have a question or a topic that you think we should discuss in a future show, please let us know. You can find a comment box below the episode show notes, or just leave a note as part of a review on iTunes.